Throughout the Linux environment, processes are nothing more than a running instance of a launched application. Whenever we execute any program, a set of one or more processes is then launched and managed throughout the operating system. Processes consist of several parts. First is an address space of allocated memory. This is something that the operating system kernel will manage, but it is something you need to be aware of is occurring. Secondly, a set of security properties are applied to a process. This relates to the ownership credentials and privileges for that specific executing program. Next, one or more execution threads of program code are launched into action. This is the intended actions when you launch a process, namely opening a piece of software, executing a set of instructions, or running through the steps of an authored script. The next thing we need to know is that each process is managed through a number of process states, and we'll look at what those states are in this section. Processes all run within their own unique environment. The environment of a process is what defines several aspects of its execution. This will include any local or global variables that are invoked throughout the running of this process. There'll be a determined current scheduling context for the process. And lastly, the allocation of system resources as managed through the system kernel will need to be appropriated. This includes things like network ports if it's communicating over the wire, or file descriptors as it creates and manages updates to and from files. We have a concept of multiple tiers of processes. The initial instance of a process will become known as the parent process. Parent processes often duplicate themselves into child processes. This duplication is known as a fork, which allows a process to duplicate its own address space and run additional processes of the same type. Each process is identified with what is known as the PID, or process identification number. The PID for each process should be unique and allows for tracking of these processes throughout their execution. When a process spawns child processes, this child process will also keep track of the parental process's process ID. We'll call this parental process ID the PPID. So in this way, a child process will have its own process identification number, but will also keep track of the parental process identification number of the process that spawned it. Here we can see that a process is created. Starting at the left, that process may proceed forward and create child processes. At this point in time, the child process is running or executing, and we see the exec statement in this case. From there, a child process can either conclude or spawn its own child processes as pertinent to the particular application and execution. Once the work of a child process concludes, it will return control to its parental process for it to resume to its conclusion. From there, the parental process will finish its work and conclude in much the same fashion. We do have several instances where a child process, or any process really, may lose track or fault in some way and can result in what is known as a zombie process. This is an unintended, orphaned process that is hard to control and is an unintended result within our operating system. Know that these exist, and we may be able to look at these throughout the rest of the sections. Processes, from their inception to conclusion, go through a number of states as they run in the operating system. Since our operating system is multitasking and managing a number of processes simultaneously, it has an elegant way of setting process states in order to determine which processes should run, in which order, and how to manage the allocation of resources from the system to allow this to occur gracefully. Here we can see a diagram that has a number of these process states defined. Let's take a look at this diagram so we can understand the states that many processes can find themselves in. From the left, we're seeing a new process get forked or created. Once created, it will be scheduled by the system. If it's ready to be executed, it can be set into a runnable state. This means it is capable to be executed, but may or may not be executing at this current time. From that state, we can either stop or resume the execution of that process, and a state of stopped would be applied. Many mitigating factors can determine whether or not we change a process state, but in the general flow of a process, we would go from runnable to running and then conclude. Several other states that happen within, in order to manage the processes and resource allocations for the system, are to stop or sleep this process. Sleeping allows a process to wait until a later point in time before resuming. It may be necessary to put the process into a sleeping state while other work concludes that are dependent on the execution of this process to resume. Once a process is completed, we'll reap those resources and return them back to the kernel for other process executions. And at that point, the process will exit. If something is lost along the way, we can end up in the resulting state of a zombie process. This is not ideal, but is something that we can manage in our operating system, or at least understand what happens when zombie processes occur. Should we have a zombie process, the operating system may have the inability to reap back the resources that were assigned to that process. Zombie processes stacking up in this order can render a system unable to process further requests because all allocated resources are locked into these unmanaged and now zombied processes. This is uncommon to occur and typically occurs only in poorly authored code or poorly administrated systems.